Hi everyone, my name is Omar Alam. I'm a research scientist working on the AQCAD team at SandboxAQ.
Hi, I'm Ji-Yoon Kim. I'm a postdoctoral researcher and I work on accelerated materials discovery and modeling through data-driven AI at SandboxAQ.
And today we'll be sharing some exciting developments on our recent work, specifically on AQVolt26, which is our high-fidelity dataset and universal machine learning interatomic potentials, particularly targeting solid-state battery applications. So large language models have risen in popularity and demand in recent times. However, at SandboxAQ, we believe that a quantitative approach to AI to model the physical world will ultimately have much bigger impact and reach, especially for applications relating to materials discovery, drug discovery, even financial institutions, transportation, and more. And so building these large quantitative models, or LQMs, as we call them, will really unlock the vast majority of our economic value, and that's our core focus here at SandboxAQ. And our particular team at Sandbox focuses on developing LQMs, specifically targeting materials discovery applications in catalysis, energy storage, and more.
Specifically in the energy sector, batteries are extremely important because they support electronic devices, vehicles, residential areas, power critical emergency services, and they stabilize the power grid with intermittent renewables like solar and wind. Driven by the clean energy transition, as well as the explosive need for data center powerhouses with the surge of AI-based businesses, the global lithium-ion battery demand is projected to reach 6,530 gigawatt hours by 2050, which is 30 times the level in 2020. However, there are roadblocks that traditional trial and chemistry cannot address quickly enough, such as preventing thermal runaway, parasitic reactions, as well as mechanical stress that hurts long-term performance, and unsustainable sourcing and disposal of raw materials that are made in lithium-ion batteries, such as cobalt, nickel, and lithium.
Modeling materials to predict their behavior drastically shortens the R&D and manufacturing cycle. And there are two approaches to this. On one hand, you have quantum mechanical methods such as density functional theory, and these model the explicit behavior of electrons using the laws of quantum physics and can accurately predict electronic properties and chemical interactions. And of course, that includes bond formation and bond breaking. On the other hand, you have classical methods or empirical methods, and these simplify this drastically by ignoring the electrons and almost treating atoms like balls connected by springs that interact with predefined equations. And these equations are typically fitted directly to quantum mechanical calculations or experimental data if available. The first approach is a bit closer to ground truth, but can be very slow and computationally expensive, while the latter is fast and much more scalable. DFT typically scales cubically with number of electrons, whereas classical methods can usually scale linearly with number of atoms. However, they are not capable of capturing reactions and also have quite limited transferability to new chemistries. So in recent years, machine learning interatomic potentials, or MLIPs, have been developed to bridge this gap by using machine learning models to sort of understand the complex laws of quantum mechanics and then apply them at the speed or close to the speed of classical simulations. And these MLIPs use more complicated framework consisting of typically graph neural networks, or GNNs, that learn complex relationships between the positions of atoms and the system's raw thermodynamic data. To give you a concrete example of what these potentials enable in practice, this is a microkinetic model for the conversion of syngas to acetaldehyde. And each point on this volcano is a different catalyst, mapped by its binding energetics against selectivity. So building this landscape originally from first principles required approximately 1 million CPU hours of DFT. Using the pre-trained potentials from the Open Catalyst project trained on the OC20 dataset, we were able to reproduce this in about 1 to 2 GPU days. And that's the promise of these universal potentials, which they enable the screening at a pace that was previously inaccessible using standard DFT methods. However, the OC20 data was computed without spin polarization, and across most of this landscape, that omission doesn't really matter. The predictions are actually quite sound. The problem here, however, is cobalt, as you can see. DFT with spin polarization identifies cobalt as the material with the highest selectivity for this reaction, and the pre-trained potentials actually miss out on that. And this isn't because of an architectural failure, but rather the data never contained the correct physics needed to describe a magnetic transition metal catalyst correctly. And the model was actually learned exactly what it was taught. And in this case, it was taught the wrong thing. This is the most dangerous kind of failure, specifically when a prediction looks plausible, however, without experimental or higher fidelity computational ground truth, you would never know it was wrong. And so our response was the AQCAT25 dataset, which is a spin polarized dataset at a higher level of electronic fidelity, as well as the inclusion of spin polarization. And it was specifically designed to try to complement the OC20 data and correct exactly this class of deficiency. So that example established a principle. Specifically, when your training data is missing essential physics, the model will fail in ways that are difficult to detect without ground truth. And the predictions look reasonable, however, they can still be wrong. But fidelity is only one axis of this problem. The other is actually configurational coverage. So what regions of the potential energy surface your data actually represents. And this becomes critical when moving from catalysis to a different materials challenge, such as ion transport in solid-state electrolytes. In catalysis, the key configurations often involve adsorbents on surface, including transition states with stretched and breaking bonds. In solid-state electrolytes, you need to typically capture ions migrating often through soft or deformable lattices at elevated temperatures over extended timescales. And the configurational demands are quite different in character, but both require training data that goes well beyond relaxed structures. So what's illustrated here is the configurational landscape sampled by the materials project relaxation trajectories. The data set that most early universal potentials were actually trained on. And each point here represents a distinct atomic configuration. These calculations were performed to assess primarily thermodynamic phase stability, and they were never really designed to train interatomic potentials. And the coverage, as you can see, reflects that. You get these narrow, clustered, near equilibrium segments, and a large portion of the landscape is really completely unvisited by the models. Okay. So now what you're seeing is the same structures, but with configurations that are sampled from molecular dynamics at elevated temperatures, and the configurations that are actually relevant for assessing ion transport. And as you can see, the coverage is quite fundamentally different. The regions that were entirely empty before are now populated. And the field has recognized this limitation and made significant progress over the last several years. So, for instance, OMAT24, produced by Meta, took an expansive approach. So over 100 million structures with Brattle geometries and ab initio molecular dynamics to dramatically widen the configurational diversity. However, MatPES then demonstrated that you can achieve comparable or even superior performance by with orders of magnitude less data, however, through a much more strategic and intentional sampling approach. The reason why this is critical is that it actually matters beyond just efficiency. So as we showed with the catalysis example, fidelity is a critical is really a critical axis here. The standard DFT methods that have been used to generate most prior data sets, often PBE or PBE plus U, typically fall short for practical discovery tasks. And what MatPES established is that you can work with substantially smaller data sets And so this frees up computational budget to invest where it counts, and specifically by elevating the level of theory, such as to r²SCAN or beyond. This enables machine learning potentials that are better suited for practical discovery tasks. So really the trajectory of this field has been toward data that is not only more diverse in configuration, but also much higher in fidelity. And this is the context for what we'll be showing you next.
So despite these strides, the potential energy surface is challenging to describe, especially when these structures we're interested in aren't found in predictable states. So in the real world, we encounter materials with shallow potential wells and anharmonic states that a simple parabola cannot capture. And so this is why we decided to explore halogenated lithium materials, which contain fluorine, chlorine, bromine, and iodine, because they're emerging in popularity due to their balance in ionic conductivity and thermodynamic stability compared to oxides and sulfides. It's a unique testing ground to develop MLPs while still covering an expansive chemical space. Halides are dynamically soft, and they present an interesting test case because it's unclear whether general purpose models can reliably replace first principles calculations within this materials class, particularly under highly distorted high temperature regimes that are required to probe ion transport. This has motivated us to investigate how we can move from qualitative to chemical accuracy for solid-state electrolyte discovery. So we used MLPs to generate 200 million configurations with machine learning molecular dynamics, known as MLMD, and we selectively sampled from a diverse set of lithium halides to generate the largest off-equilibrium dataset for solid-state electrolyte materials using a higher level of theory. Universal models were co-trained with foundational meta-GGA datasets with state-of-the-art architectures, demonstrating superior performance for materials with applied strain, stability during MD simulations, and more accurate ionic conductivity values relative to experimentally validated results. To create the AQVolt26 dataset, we prioritized lithium halogenated systems that are free of radioactive elements and noble gases. These were largely sourced from the Materials Project and the MatPES r²SCAN dataset, but we generated even more compounds through halide anion substitutions and by inserting lithium in halides that were previously lithium-free with redox-active metals that could accommodate the additional charge, which resulted in a total of 4,911 systems. We then ran MLMD for trajectories up to 50 picoseconds long at temperatures above 300 K to generate 200 million configurations, 8.5 million of which we prioritized for configurational sampling. We leveraged a recently published strategy called 2Direct, where the structural and atomic features are encoded, resulting in billions of descriptors in large vectors to represent the vast feature space. Principal component analysis was then performed to reduce the vector dimensionality by capturing the maximum variance in the data. And a centroid-based clustering method was applied to group similar configurations, and structures were sampled in a stratified manner to choose the most distinct features among the clusters. So as a result, with this method, we were able to perform DFT on only 2% of the trajectories to efficiently represent the configurational diversity, which is a significant expansion of the current lithium halide structural and chemical landscape. Combined with some ab initio MD simulations we performed, we created a high-fidelity, off-equilibrium dataset of 323,000 single points using 5 million CPU hours of compute. Alongside recently published r²SCAN datasets such as MatPES, MP-ALOE, and the Materials Project Trajectory, we co-trained AQVolt26 with the equivariant smooth energy network architecture, adopting a multi-stage training protocol. And we performed comparative first principles benchmarking of various models across datasets, binned by maximum force magnitude, to reveal how predictive fidelity changes as systems move away from equilibrium. While the local potential energy surface curvature transfers relatively well across chemical domains, absolute energy predictions exhibit massive degradation without direct exposure to these distorted atomic environments. But co-training with AQVolt26 explicitly resolves this high temperature blind spot. While incorporating extreme off-equilibrium geometries into the training distribution improves dynamic robustness, exposing models to heavily distorted, high-temperature configurations can degrade their precision on strict 0 Kelvin equilibrium tasks. So to evaluate whether these models suffer from this trade-off, we benchmarked their ability to reproduce r²SCAN DFT structural relaxations, and we found optimal performance for non-lithium halides with explicit co-training using near-equilibrium materials project data to bridge the gap. So having established that optimally trained models maintain fidelity at equilibrium, we evaluate the potential energy surface under extreme hydrostatic strain with an energy volume scan benchmark developed by MLIP Arena. So with this EV-scan benchmark, we confirmed that the AQVolt26 MatPES and MP-ALOE ESEN model possesses exceptional stability with only a 0.1% failure rate when subjected to both negative and positive uniform lattice deformations up to 20%, which outperforms several state-of-the-art baselines. We also tested their performance in dynamic, high-temperature environments on out-of-domain samples, where we see higher survival rates with our AQVolt26 trained models. Overall, we show that AQVolt26 produces an order of magnitude improvement on the intended off-equilibrium halide regime, while preserving competitive performance on established foundational benchmarks. With this dataset and state-of-the-art models, we are able to further develop next-generation MLPs and accelerate materials discovery with unprecedented accuracy and speed. So our models will serve as an improved baseline to streamline future innovation and even serve as improved computational inputs to explore multi-scale simulations and to better predict downstream properties in batteries that are more relevant to the current challenges faced in the industry. If you're looking to dive deeper into AQVolt26, you can scan this QR code and access our latest models, as well as a tutorial to help you get started on Hugging Face. Our full manuscript is also live on arXiv. We are incredibly proud to highlight our core partners in this journey, NVIDIA and Google Cloud. Their infrastructure and collaborative spirit have been instrumental in creating this dataset and training our LQMs. If you have any specific questions or you're interested in a potential collaboration, please don't hesitate to reach our team directly at materials@sandboxaq.com. Thank you for your time today, and we hope to connect with you soon.